Hi there, Mr. Sutton bringing you this lesson on similar polygons. In this one, we're going to find missing measures in similar polygons, and we can use this to figure out the perimeter of a new pool. Before we get too far into this lesson, let's do this warm-up here. We're going to try to solve each of these equations. Now, just before you start solving this, a little bit of a definition here. In this situation, when you have two fractions that equal each other, we call this a proportion. So that's two fractions or ratios that are equivalent. So pause the video and see if you can solve this proportion. All right, did you remember how to do this? You might remember that we need to cross-multiply to solve one of these. That is to say, you can multiply the denominator of one fraction by the numerator of the other, and you just do that both ways. It makes a nice little cross kind of shape. So we can write 10 times x equals 6 times 20, or 10x equals 120. And then we just have a regular equation that we can solve by dividing. So dividing by 10, we have x equals 12. All right, on this one, a little bit trickier here, we have more than one term on the denominator of both of these fractions. If you have multiple terms on one side of a fraction, you have to distribute in that situation. So this is really 3 parentheses m plus 1 equals 2 parentheses m plus 5. And it's up to you whether you show this parentheses step, but you still have to distribute. So that'll be 3m plus 3 equaling 2m plus 10. Subtracting the m's, we have a 1m on the left. Subtracting 3, we have 7 on the right. And that just so happens to give us the answer. Nice. Now, one other thing I'd like us to do here is to check our answer in this one, just to see something that's kind of neat. So if we plug 7 back in for m, we have 3 over 12 equals 2 over 8. Well, hold on a sec. 3 over 12 and 2 over 8, those aren't the same, or are they? What do we get if we reduce these fractions? That's right, we get 1 over 4 in both cases. So these are equivalent, they are in the same ratio. And this idea of having things that look a little bit different, but they're actually the same ratio, this is what similarity is all about that we'll see in a sec. So our algebraic review is over. At this point, we're going to start talking a little bit of geometry here. We're going to compare congruent and similar polygons. Now, before we can do this, we need a little crash course in congruence, or at least a review. So congruent polygons, and this is the congruent symbol here, a little equals with a tilde squiggle over it. These polygons, and here's an example of 2 of them, have the following features. So you'll notice from these diagrams here that they have all the same angles. These little arcs here tell you which angles are congruent, like these double arc angles go together. So we have all the same angles, which gives us the same basic shape. In addition to that, if you look at these little hash marks, which tell you the sides that are congruent, they also have all the same side lengths, which means that they have the same size as well, so same shape and size. Now, when we want to tell people that 2 polygons are congruent, we write what is called a congruence statement. So here is one such statement for these 2 triangles over here. We could say triangle ABC is congruent to triangle DEF. Now, I didn't just write these letters in some random order. Take a look at angle A versus angle D. Here's A, here's D. What do you notice about them? What do you notice about angles B and E right here? How about C and F? So I wrote these in the same order of congruence in terms of the angles. I mean, I can write one of these in any order I want, but once I pick a certain order for one of these, I have to follow suit and put the congruent angles in that same order in my other shape here. So that's congruence in a nutshell. Let's talk about something similar, no pun intended, similarity. So similar, this is giving a symbol of just a tilde here. There's no equals. Because these are not equal in the way that congruent polygons are. But there are some similarities. Hate to keep using that word. Here's 2 similar figures for you to look at. Now, what do you notice about these figures versus the figures up on top here? These figures still have the same shape. We still have all the same angles. And one is kind of a miniature version of the other because they have the same shape, but they don't necessarily have the same side lengths. Now we say that the sides are proportional. That's what this same shape business is all about. But they could be different lengths. Now, similar polygons, there's a similarity statement you can write, And it's actually pretty similar to the congruence statement up here, but we use a tilde instead, and we still write the angles in order of congruence. But we understand that this means these shapes have the same shape, but not necessarily the same side lengths. Let's do an example now where we apply all the different facets of similarity to find a few missing variables. In this one, we're given these two similar triangles. How do we know they're similar? Well, they told us up here that they were similar. And we're asked to find side x and angle y. Let's do the angle first because that's by far much easier. Remember from before, similarity means that we have all the same angles, congruent angles. So we just have to figure out what angle this y angle corresponds with over here in the other triangle. Now you can look at the shape of these triangles, and that's a good tip-off, but to really be sure, you want to look at this similarity statement up here. So this goes with angle E. Angle y is really angle E, and angle E is the second letter in this statement, so that means it's going to be congruent to the second letter in the other triangle, which is this n over here. So since angles E and N are congruent, we know that y has to equal 35 degrees. All right, let's tackle x now, which is a little bit trickier. So because the sides of similar figures are proportional, that means we can actually set up a proportion between the sides. That's really what proportional means mathematically. So the way we're going to do this is to set up and solve a proportion that has the missing side and its corresponding side, and then one other pair of known corresponding sides. So for example, in terms of corresponding sides, we know that this x side and this 20 side go together. Now, how do we know that? Well, I mean, you could look at the shapes and kind of intuit that from the diagram, but again, to really be sure, you can look at the letters. X is really side EF, so that's the second and third letters in your similarity statement. That goes with NP, the second and third letters in the other triangle, which is this 20 side over here. And then 9 and 12 also go together. Now, they gave us this 16 side here, but we don't know anything about that side in the first triangle, so we're not even going to look at that one. So let's set up a proportion with these now. There's a couple ways we can do it. One way is to put the corresponding sides in the same fraction. So we can write x over 20 equals 9 over 12. Another way you could do it is put the sides from the same triangle in the same fraction, as long as you do it in the same order. So you could also write x over 9 is the same ratio equals 20 over 12. Either way, we've got to cross multiply. So pick one of these, cross multiply it, and let's see what we come up with. All right, so cross multiplying in both cases, we're going to get a 12 and an x multiplied together. And the only difference here is the 9 and 20 are kind of kitty corner from where they were before. Either way, that still comes out to 180. If we divide 180 by 12, we get 15 for x. Here's another example involving similarity. We're given two similar quadrilaterals here, and we want to find the values of A, B, and C. Pause the video and give it a shot. All right, let's see what you came up with. So I'm going to go in alphabetical order here. The angle is by far the easiest to find, but we'll do that one last. So finding A first, I notice that A is going to correspond with this 40 side over here. So A over 40 is going to be one of my fractions. And then I need to pick another pair of sides in the same order that I also know about. So this 40 and this 32 also correspond. So I can write A over 40 equals 40 over 32. And I didn't have any other complete information. There were no other complete corresponding pairs, so I really had to use this here. So cross multiplying now, we've got 32A equaling 1600. And if you run that on the calculator, or maybe you could do it in your head, either way, that comes out to 50 for A. Now that you know A, you could, if you wanted to, use 40 over 50 or vice versa to figure out the other missing side here. Or you can just go with this 40 over 32 that already worked for you with side A. Now, honestly, I would go with 40 over 32 just because they gave you that in the problem, so you know for sure that that's correct. This A value, maybe you got it right, maybe you didn't. If you got it wrong, then you're just getting more wrong answers if you continue to use it. So let's use 40 over 32 again. This time, we're going to find b. So for b, I'm going to write b over 16. So 16 times 40, that's going to be 640. Or actually, nope, I'm right, 640. And then we'll have 32b. Dividing by 32, we've got b equals 20. And now it's downhill from here. We just have to find this C angle here. We know that G and Y are congruent. I mean, they look congruent, but you can't always go by looks here. Looking at our similarity statement, we've got G and Y as the last letters in both of these. So that means that C has to equal 49. For our next example here, we're going to hit a few new concepts. We have a hotel building two pentagonal pools such that this pool and this pool are similar. First thing we want to do is find the scale factor of pool ABCDE to pool FGHJK. So what is the scale factor thing? So the scale factor is basically just the reduced ratio of any two corresponding sides. So you just have to pick two sides that go together from each of these shapes and see what the reduced ratio of those would be. The only two sides that we know that go together are this 10 and 15. And again, we know those go together because if you look at the similarity statement, AB and FG are the first and second letters in each of the shape names. So we can then write that the scale factor, I'll just say SF for short, equals 10 over 15, which we can reduce to 2/3. So why do we care about the scale factor? Well, it is a little bit of a shortcut sometimes. If you know the scale factor, then you can use it to find missing sides in proportions. So if you look back at the last page here, when we were solving these two shapes, if instead of using 40 over 32, we could have just used the scale factor of this shape to this shape. We could have just used, this would have been 5 over 4, which might have made our cross multiplication a lot easier. So just something to think about as you're doing these. Sometimes it's nice to find that scale factor. All right, moving ahead now, we want to find the perimeter of each pool. So let's start with the pool that we actually can find the perimeter for. That's this larger pool here, or at least it looks bigger. So if we add all those numbers together, let's see what it comes out to. Let's see, we've got 24, 36, plus another 15 is 51, plus another 18 gives us 69 for the total perimeter. Now they want the perimeter of that smaller pool. Now there's a little bit of a problem here. They did not give us all the sides. Of course, you know the scale factor of this pentagon to this pentagon. So one option we would have would be to go through and set up proportions and solve for all of these missing sides. That does seem like a lot of work though, doesn't it? I mean, that's 4 different sides you're going to have to solve for before you even get to add anything together. The good news is that all length measurements of shapes are similar. If the sides are similar, then every length measurement is going to be similar, including perimeter. Perimeters then are also going to be in proportion. So rather than solving for each of these sides individually, we can just set up a proportion with the perimeter we know, the perimeter we're looking for, and the scale factor. Let's let a letter stand for the perimeter we're looking for. Let's let P be this smaller perimeter, just so we don't have to keep writing perimeter of A, B, C, D, E. So our proportion then, we can say P, that's the smaller perimeter, over 69, the perimeter we know, the perimeter of this larger one, equals 2 over 3. Because again, we set up our scale factor by doing a side from here divided by a side from here. So pause the video and cross-multiply that out. All right, so we end up with 3P equaling, this will be 138. And then if you divide that either by hand or on a calculator, we end up with P equaling 46. A lot faster than finding all of these, right? We're going to do 2 more examples now involving triangles formed by parallel lines. Now, the neat thing about parallel lines and triangles is that they tend to create similar triangles. How do we know they create similar triangles? Well, similar triangles are triangles that have all the same angles. If you look at this smaller triangle and the bigger triangle of which it's a part, well, they definitely both have this angle R in common, right? It's the same angle for both of them. But we can also show that this Q angle here and the U angle are the same. When you have parallel lines, these corresponding angles we know are going to be congruent. And the same thing over here. If you have angles on the same street corner of parallel lines, we know those to be congruent. So that means we can set up a proportion on this one. So set up a proportion that you think you could use to solve for x. Do you have one? All right, so you've got a few options here. One way you could do this is you could say, x over x plus 9, small side over the bigger side, equals 4 over 10. You actually don't even have to do that much work, though. You can actually just write x over 9 equals 4 over 6, and it will come out to the same thing. So it's actually, you're just kind of like putting these in the proportion the way that they're laid out in the diagram. So it's really neat how this works out. Cross multiplying, we have 6x equals 36, so x equals 6. And just in case you don't believe that this was legitimate here to just do x over 9, let's see if this is actually in proportion. So if you had 6 over 15, is that the same proportion as 4 over 10? Well, 6 over 15 reduces to 2/5. 4 over 10 reduces to 2/5. So, yep, it does actually work. We're going to do one more of these parallel line triangle examples. This one's a little bit trickier, though. So we have the parallel lines. We're going to have similar triangles. We definitely have these vertical angles in the middle that are equal, and alternate interior angles out here are also going to be congruent. The trick on this one is to figure out which sides correspond with which. Because if we set up a proportion wrong, even if they're proportional, we're going to get the wrong answer for x here. So what I would recommend you do is, first off, mark the congruent angles to see which sides correspond with which. So again, we know these vertical angles are going to be the same. We know that these alternate interior angles, A and D, are going to be the same. And then E and C go together. So I'm just going to look at the sides that are across from angles with the same number of arcs. In other words, across from congruent angles. So for example, BA, which is across from the triple arc here, has to go with BD, which is across from the other triple arc angle. And BE, which has the side I'm actually looking for, that's across from the double arc angle, that's got to go with this BC side, which is also across from this double arc angle. Now that I've written that out, I'm just going to actually plug in the values. So we had 18 over 30, BA over BD, equals x over 15. And it's just cross-multiplying at this point. So we have 30x, and if you do it by hand or on the calculator, 18 times 15 gives you 270. Dividing by 30, we get x equals 9. So that's it for this lesson on similarity. Till next time, this is Mr. Sutton signing off.